Unfortunately, almost it's my last lecture. Unfortunately, because what I want to talk about, I think I would need at least two. So I'll try to, well, rather than compressing, I'll try to removing things that may not be completely necessary. So it's another capacity and another technique. And it's even a different result. It's called a pretty strong converse, which is not quite, it's not really strong, but not weak either. And the technical, so it's basically a pretext to talk about min entropies, min and max entropies. So the main thing is I want to talk about quantum capacity. So recall that what this was. We are allowed to encode information and decode. So this is the given channel, and this E and D, these are operations that have to be implemented by the sender, respectively receiver of the information. And I draw this diagram with a maximally entangled state of rank R, such that this state here, so let's say, so here we have A to the N, so n copies of system A, B to the N. What goes in here is basically our system on which we want to send quantum information, so we call it S, and then we have a reference system here. So this is a state sigma SR, and this should be close to phi A, right? And in the very first lecture, I suggested, okay, we should demand that the so-called purified distance between these two states is small. So on an intuitive level, you might actually I might as well have chosen the trace distance, but I mean it's just a conventional thing, and it somehow it makes certain arguments nicer. I mean, but it's likely that we do not even get to see this in this lecture at work. So nevertheless, I mean, I just want to stick with it, mostly because I want to refer to a preprint that contains basically all of this, and probably it's even more digestible than what I'm telling now, because I'm trying to squeeze it all into 90 minutes. So the maximum for given epsilon, we're interested in the maximum of L over all possible encodings and decodings, and so this is then L of n epsilon. And so as usual, we are interested in the asymptotic behavior of this. So let me put it this way, so then I just yeah. Sorry, this should be a log. So the log of L is the number of bits of entanglement we can create, and so this requires that n goes to infinity and epsilon goes to 0, obviously. So why I'm writing this, what you should remember anyway, is because I want to remind you of this formula that we have for this. Where Q1 is the coherent information of the channel, so this is the maximum over all phi, and I will draw a little diagram here, maybe a little bigger diagram. phi, and here we have rho. So this is A. Put like this, and we have the negative conditional probability, conditional entropy with respect to rho. So and another thing that we saw repeatedly in the last few days is this limit is really necessary. We know that Q is not equal to Q1. Q1 is super additive, so Q1 of n copies of the channel is at least n times the one copy quantity. And there are examples where n copies can be strictly, this here can be strictly larger than n copies of Q1 of, n times Q1 of n. So, so this is just a remark. So Q1 is not additive, and Q1 in particular is different from Q in general. However, and this is Q of n equal to Q1 of n if n is degradable. Yeah, so this, I hope you remember this concept. I'll get to this again, because this is the motivation that for concentrating on degradable channels only for most of the rest of the lecture. So so to be precise, the result, the big result that we can prove, it only applies to degradable channels.
Andrea, can I ask you a far-fetched question?
Please.
I know this regularized Q can be larger than Q1.
Yeah.
But is there a limit on how much it can be larger? I just want to know, if one has a materialistic attitude,
yes,
what kind of great profit that one is sweating through? You understand what I mean?
Yes, yeah. Well, okay, so the very first
fundamental limit on this difference.
Well, yes and no. I mean, so for example, recall that, so the very first example for this here, this is Shor and Smolin. They look at n, a depolarizing channel, and with appropriately chosen noise, and they find that you can, Q1 of n is 0, and Q1 of n tensor n is very small but positive. So in a certain sense, the difference, of course, is this minus that is small, but the relative difference is infinite. So I don't know what to say to that. I mean, I don't.
Well, I think you have answered.
Okay, if you're happy with that, then we leave it at this.
Just to understand, what is sigma SRI?
So this is the output state. This is the state that we have here. So I don't want to write it down because I wrote it down a few times already. So I want to make a little observation that actually we do not need this encoding here, because let me call this. So of course the encoding is this here. This encoding, the way it's defined, it can be anything. It can be a noisy CP map. When you look at the arguments that lead to this formula here, the achievability part, we only use unitaries here, or isometric embeddings. But I mean, a priori, there's no reason to think that this is optimal. I mean, there might be some sense in which a noisy operation can do something for you, even though it turns out later that it doesn't. Anyway, so whatever this does, we have a bipartite state here. We have some kind of rho R A n here. And so whereas this diagram here that corresponds to transmission of information, there is this kind of relaxed notion of an entanglement generating code. And so the code it simply requires this state rho, R A to the n, and the decoding. Yeah, so it's just these 2 bits, 2 pieces of data that we need. And then we can still ask for how close is the output state to the maximally entangled state. So and basically, motivated by this criterion, where I'm not asking that whatever the state. So just rolling back a little bit, I'm not asking that every state that I stick in here comes out with high fidelity. I'm just saying at the end of the day, I want the maximally entangled state. So let's take this literally as our goal. And so then the max of L of these sets, of these pairs rho and D, this is then, let's call this, I don't know, L tilde of n epsilon. And this can be larger or equal than n of L of n epsilon. So it turns out that the limit is the same. So in that sense, it doesn't make a difference. The integers, they can be different for a given n and for a given epsilon. But in the limit, we are getting the same thing. So from now on, I will focus only on entanglement generation simply because it's simpler. It's easier to reason about it because I get rid of this map and I replace it by a state. In fact, here's a little exercise to think about. Without loss of generality, rho, so the input state, rho of an entanglement generating code is pure. So rho is some kind of phi R A. Okay, so so let's see what we can do today. In my original plan, I also wanted to. Okay, so let's put this also as an exercise. In my original plan, I also wanted to talk about a simulation argument that is adapted to this kind of things. So and so the simulation argument always has to start with the ideal channel. So we consider the noiseless qubit channel. And in fact, even assisted by classical communication. So if you want there can be even some kind of classical communication going on the side of the channel between the E and the D here. In fact, it can even be two-way. So it can be I mean, we're actually talking about an LOCC procedure between Alice and Bob in exactly the sense that Eric's talking about it. So I want to show that this entanglement-assisted maximally the maximal Schmidt rank that I can get for entanglement generation, and so this is kind of let's call it LOCC of n. I mean, I hope this is suitably defined. Defined I mean, following the words I just said, right? So this is less than or equal than I think something like this here. I worked this out somewhere. So this is the kind of thing that we saw also for the classical capacity, that the number of messages is essentially 2 to the n, because that's the dimension of Hilbert space we have, and then there is a little bit of a factor that comes from the error we allow. But of course, once we take the log, this just splits off as an additive term, so it actually gives you the strong converse. And of course, L is less than or equal to L tilde is less than or equal to L tilde LOCC. So it's because we are allowing more and more, we are relaxing the problem more and more. So if you can prove that, then you also prove it for the original entanglement generating code and for the transmission code. And then there is a last one. So so recall that, I think that is something that Graham discussed at length, the 50-50 erasure channel has capacity 0. Yeah, so erasure channel means do I have to write it actually? Well, maybe it's always better to write the definition, no? So E 1/2 of rho, or E in general E Q, is with probability Q the state comes out unchanged, and with probability 1 minus Q it goes to some erasure symbol. And I just want, I write a direct sum here to insist that this state is orthogonal to all the rows that we have. So whatever the input dimension of this channel is, the output dimension will be 1 larger. So for example, qubit Q3. So in 50-50 simply means this is 1/2, right? So it should be clear. So the question that I have for you is, so why does, no, sorry. So, I mean, this is a good test case for the simulation argument, because the simulation argument, it requires, we want to use this. We want to say, let's try to simulate a channel, and then with a number of noiseless ones, and then of course we get an upper bound on this L here. So the question is, what is the simulation cost of this? In terms of as qubits per channel use. And I can even allow you to assist by classical communication, because this simple argument allows that, right? So we can include this. So why I'm asking you this exercise, because you will find that this cost is non-zero. So I want you to think about why that has to be. So we'll skip all these things. I think I'll have to go back to this degradability now. So I want to show that for things like the erasure channel, we are able to get something like a strong converse. We get some good bounds on the amount of information you can send, independent of epsilon. Right? So that's what I always want for these strong converses. That's why this last part is very important for me, because it shows that this kind of simple-minded argument, reducing it to identity channel, it won't work. Erasure channel is, by the way, degradable. So from now on, we only look at these ones. So that is, if we, let's introduce the Steinspring isometry once and for all. So then we have the n complement of rho, so that's this here. This can be obtained from the output of n by a suitable degrading map. So this is the definition of degradability, and obviously, so you can check that for q less than or equal to 1/2, the entanglement breaking channel is the erasure channel is degradable, and in fact that the complementary channel is also an erasure channel, but with the opposite erasure probability. So, for example, EQC is equal to E1 minus Q, or isomorphic. I mean, that's kind of, you can check that. Okay. What is it? Devetak Shore's original proof that, or at least some variation of it, that is, which is the key to calculate the quantum capacity for degradable channel, which is this additivity. So Q1 of n tensor m equal to Q1 of n plus Q1 of n for degradable. And so notice that this here is what I would call the trivial direction. So this always comes from the additivity of the entropy. So you can, I mean, if you don't see this right away, then consider it as another exercise. So this is always true for any channels. So in this direction, we have to use the degradability, because we know that, for example, for depolarizing, as I said before, it's not true. So look at this here. So this is our channel in the church of the larger Hilbert space. I have to use degradability. Well, so let's just apply the degrading map. So the cool thing about keeping all these unitaries, or more generally isometries, is that I'm never really losing or destroying information. I'm just shifting it around. So if I want to see B, for example, all I have to do is I have to look. I just have to kind of stop the film here. But I don't have to do this, because this is just a unitary that gives me E prime, which is just a copy of this system here, and then something else. So yeah, this is the channel, and this is the degrading, which also is a CP map. So it has its own Steinspring dilation. And so the argument, somehow this is very fascinating, that we have two copies of the environment here, right? So it's obviously not cloning, because I'm not saying that the same state is here. What this means, two copies of the environment, is that whatever I stick in here, it's going to be correlated in this from between A and E. The correlation will be the same as between A and E prime. So that limits the kind of correlations that we can have, because we cannot choose what output state is here. So there are only certain mixed states that can appear here, and then the same one appears here. Maybe they are also correlated amongst themselves, but they were not talking about this. So here's a fact. I would like to use this thing that these guys are the same in a certain sense. So what about applying a swap here? And that's a unitary. And I would like to compare this, what this thing does with a swap. And so that's not always possible. And the reason is that these Stein-Spring dilations are not unique. I mean, they're unique up to a well-known, well-understood set of isomorphisms. But we have a choice here, and also here, for the degrading map. In fact, the degrading map itself as a CP map may not be unique. Generically, it should be, but sometimes it's not. So it is true that it's possible to choose these maps. To choose V and W, subject to that V is a dilation of the channel and W is a dilation of the degrading map, such that, now let me see, W tensor identity, so this would be identity acting on E, followed by V, is the same, is virtually unchanged. It's the same map if I swap E and E prime. Is that what I need? Well, okay, I guess that's what I want. Yeah, and this is possible. You cannot just cancel V because it's not an isomorphism, it's just an isometry. So it maps A into some subspace here, and so this only expresses some identity with restricted to a subspace of here. So that is a very important step. So I will not justify this because it requires a bit of algebra that is ultimately not so interesting. It's a bit boring. But it justifies this idea that we have that E and E prime are completely equivalent. We can just substitute E for E prime and vice versa in any kind of part of calculation if we talk about this final state. Okay, so of course we have such a thing for both a channel N and M. Oh well, let me do something. I change here in 1 and 2. And so with V1 and V2 and W1, W2. So now I have to evaluate this coherent information for the tensor product. So here I have V1 tensor V2. I have some test state here. So this is A1, A2, B1, B2. Then I have the product. Obviously, if I have a product of degradable channels, it's degradable because I can use as degrading map just the tensor product of the individual degrading maps. So what do we have to look at? We are interested in this. This Q1 of the tensor product. I have to look at the negative conditional entropy of A1, A2 given B1, B2, and that of course refers to this state here. Yeah, because I need to mention B1 and B2 here. But I can just invoke this isometry, so I can write this as minus S of A1, A2, given sorry, I don't want to waste too much time. So let's first do this part for the single channel. So minus S of AB, and so this refers to here, so we have a state we have a state phi here, and let's say we call this here psi. So this, again, I mean, I'm just applying this unitary, so I get an E prime F, and then I have this psi. So this is what I said before, this is the use of keeping track of everything in a big pure state, because then you never lose information. So you can express everything always somehow at the very end by just collecting the right systems here. And so E prime F together is the same as B. And now we are using, and now we are, so I'm doing the Devetak-Shaw proof, only that it's a bit more complicated than necessary. I'm using a chain rule for the entropy. So this is S of E prime F minus S of A F given E prime. So chain rule, this looks like this. S of x, y given z is equal to S of x given z plus S of y given z and x. Yeah, so you can see this applies here because I just want to shuffle around three systems. Oops, so this is completely wrong. So this should be F given E prime. Sorry. And okay, so then we have this nasty term here, but now we're going to make use of the fact that the only other system here is E. So let me put this here. So this is equal to, so including the, well, okay, let's not move. So this term itself is equal to minus S of A F given E. And that's because we have a global pure state. So you can convince yourself this is a property of the entropy if you replace in a conditional, if you replace this part by all the rest that you need to have a pure state, then you just change the sign. But now we use the symmetry. E and E prime are the same. So this is minus S of AF given E prime. And so that means that it's equal to 0, because it's the same term only with a minus sign. And so I could have done this a little bit easier, but the thing is I wanted to show that I can do this only with conditional entropies. So this is kind of an important next step. So this looks very baroque at the moment. Previously I was very happy to expand everything in terms of phenomenon entropies. So for example, this one here, we know that this is a difference of entropies, right? You should recall that this is entropy of AB minus entropy of B. So anyway, this is S of F condition E prime. So now we can go back here. So this is the same kind of situation, only that everything has an A1, A2. So I get that this is equal to S of F1, F2, conditioned on E1 prime, E2 prime. And if I want, I can even drop the primes. But it's nice to see that I can get this state here by just applying the channel and then this isometry. So this refers to only a state which can be written as W n of, let's call it rho A, W dagger. And so here I have a reduced state rho A1, A2. And so now I can do, I mean, I'm just doing something very slowly that Graham was hinting at very briefly last week. Again, we have, for the entropy, we have strong subadditivity. Strong subadditivity for the entropy is basically the same. I mean, what it really amounts to, I mean, if you think information theoretically, you should really always think of it as it's the subadditivity of the conditional entropy. So again, just for the sake of the argument, I want to do things in such a way that I will always ever talk about conditional entropies. This will be, I mean, the reason why I'm doing this is because we know already that we can get weak converse for the capacity from reasoning about entropy, but we will have to go to these min entropies, these min and max entropies. And in fact, these are conditional objects, and there is no way to relate them in a good way, let's say. I mean, there's a way, but it's not a useful way to relate them to entropies. So we somehow have to remain in this world of thinking about conditional states and conditional probabilities, conditional entropies. So anyway, Strong's additivity is this here, that S is less than S of F1, condition E1 prime, E2 prime, plus S of F2, condition E1 prime, E2 prime. And then there is another manifestation of Strong's additivity, which is that if you drop one of the conditioning systems, the entropy goes up. So that in the classical probability, this corresponds to this idea that if you lose information, your uncertainty goes up. So this is again Strong's additivity, and in fact twice. This is less than S1, SF1, E1, plus S of F2, E2. And so this is nothing else but minus S of A1. So this is less than or equal than Q1, let's put it this way, N1 plus Q2 of N2. Yeah, something like this. So, and since we want to take the maximum, this can be at most the Q1 here on the left-hand side. So that's how the proof goes, using only conditionals. So I can show that this is 0 without expanding it in terms of entropies, but just using it as you want, if you want, as an axiom that I have this complementation rule. So S of A B is minus S of AC with respect to a pure state psi ABC. So this is another of these identities that I'm using here. Okay, so these min entropies, this goes back to well, it goes back a long way, but in the form I want to use this, I mean, in the particular form that I want to employ them, this goes back to Renato Renner's PhD thesis, and it's on the archive, luckily. And it was further developed, I mean, much developed in subsequent years. So this is already 8 years ago now. By his student Marco Toma-Michel, whose PhD is from. Oh yeah, I hope I have this somewhere here. Let me just put the reference here. Ah, yeah, okay. So in his PhD thesis in 2012, this was much developed, and so the purpose of this is why this turns out to be useful, because every single step in this argument here except for the very last one, where I try to break it up into a sum of two terms. It has an analog in terms of mean entropies. So if you want, so the rationale for these mean entropies, or rather conditional mean entropies, is to introduce an alternative functional, very much like those Rényi entropies I talked about yesterday, to introduce such functional that is different from the entropy, and in a sense gives, behaves differently in a significant way, but still shares some of the elementary properties, like invariance under unitary, or this chain rule, or this complementation rule, and so on. So I want to preserve some of these quantities so I can go through the same argument. But of course I need also some other properties that allow me to do the first step. That was not so trivial to relate this number to the log of the maximally entangled state that we can get out from all of this. Okay, so I start with the definition, and let me see how much time I have. So I just write this down. Yeah, okay. So these quantities, they always refer to bipartite states because it's supposed to be a conditional thing. No, let's put it like this. Maximum lambda such that rho AB is less than or equal to 2 to the minus lambda identity A, and so sigma B. And sigma is a state. Yeah, so by absorbing this here into sigma, then this is just a positive factor. So we are left with a positive semi-definite. This is the same as minus log of the minimum trace S, such that rho AB is less than or equal to 1 tensor S. Okay, I put this over here, and so then we have actually it turns out for these so these kind of entropies, they are sometimes called one-shot entropies. They are like Fernando talked about this at least to some degree last week. They are meant to capture properties of the state in a situation where you do not have many copies of the same state. So you should appreciate why this is useful, because we're going to use here the channel n times, so the V tensor n and the W tensor. Sorry, forget about the W. We want here at this point, Bob wants to decode, but the code. So the channel, of course, is many copies, but the code is whatever it is. I mean, Alice will stick in some state, and Bob will make some global operation to get out the entanglement, and neither of these data has any relation to the tensor product structure of the channel a priori. So the state we're going to see here, it lives on n copies of A, n copies of B, n copies of E, but it has no tensor product structure whatsoever a priori. And so we'll have to deal with it. And this is what the entropies are bad at, and these mean entropies are kind of designed for. But the price is you get two of them somehow, at least apparently. No, sorry, I don't want to trace. And I guess there should be a square here. So there's a fact or a fundamental lemma. Let's put it a fact because in this way I don't have to prove it. H min of A given B is equal to minus H max of A condition C for pure psi ABC. And so then taking here the reduced at AB and here the reduced at AC. So this is a fact that that comes out of by analyzing these two optimization problems. So just, I mean, let's take it as an axiom. So you see this is going to replace, this is going to be useful in this part of the argument, because we will be able to substitute for a system, its complementary system in a multi-party situation, and change the sign. But of course, the price, we always pay the price somehow with these min entropies. Then we have to deal with max instead of min. And the other thing that we do is, now this is necessary to incorporate those errors, these deviations in the code, because I mean we want to analyze a situation where we do not get a maximally entangled state, but we get close to one. So it turns out under small perturbations in the trace or in the purified distance, these numbers, they do not behave well in the same way as the entropy behaves well. So there's this continuity bound, the Farnes inequality. Instead, these guys here, they can change quite a lot, even under minuscule variations of the state. So what we do is, we basically impose continuity, at least on the level of epsilon. And so H min epsilon is simply the largest value that you can have in a neighborhood of rho. So if we, I mean, this always refers to a state rho, right? So we have H min of A given B rho tilde. And then we look at rho tilde such that the distance of rho tilde from rho is less than or equal to epsilon. And the same, oh no, not the same, actually for H max. Yeah, this is initially a little bit confusing. So in the definitions, H max is a maximization, and up to this minus sign, H min is some kind of a minimization. But when I do the smoothing, I want to make H min bigger. So there's a conflict here. I want to maximize. H max of AB, rho with epsilon, is defined as the minimization of a rho tilde with its distance, H max, sorry, A, B.
The distance you're using is the one now?
I'm using the purified distance. So purified distance of rho tilde rho is square root 1 minus fidelity squared. So there is, yes, please.
Definition of mean entropy.
Sorry?
Definition of mean entropy.
Yes?
Second line. What is S? S is positive or state density matrix?
S is just positive semi-definite. Yes, yeah, yeah. So you see that this between this line and that one, all I'm doing is I'm multiplying 2 to the minus s with sigma. So the trace of s comes out as 2 to the minus lambda. Sorry, 2 to the minus lambda. So, okay, now I can show you why I want the purified distance, because this is one of the discovery of Renato and his school. Because in this way, the duality relation, so this what we call duality here, for the min and max entropies, it carries over directly to the smooth min and max entropies. So so here's another fact or exercise. So whenever you have two states, so for all rho and sigma, you can find purifications. So pure state, I mean, on whatever system, you can find purifications, phi and psi, of these two respectively, such that P of rho, rho and sigma is equal to P of phi and psi. which is actually it's equal to the, which way does it go? It's equal to the minimum over all purifications. P of, maybe I should say phi 0, something. Yeah, so this second one is because P is contractive. So like the trace distance under completely positive maps, including the partial trace, the purified distance can only decrease. So whenever I have two purifications of rho and sigma, then the distance between these is larger or equal than the P of rho and sigma. And the claim is you can actually find that they're equal. So this is Ullmann. This is so-called Ullmann theorem. Because well, basically, it really refers to the fidelity. So in fact, using this, you can convince yourself that this implies that H min epsilon of A, B is equal to minus H max epsilon of A, C. So these are the definitions. And okay, I started already with some of the properties. So I mean, this property maybe is very important because it actually shows that really we only, I mean, on a fundamental level, we only need to understand one of the two because they're always related by this duality relation. But nevertheless, it's good to remember these kind of formulas. So I believe that Fernando only talked about min and max entropy, period, without conditioning. So that is included here in the case that the B system is trivial. Or more generally, that the state we're talking about is already product between A and B. Because if you have a rho AB here, rho A tensor rho B here, you may, for example, always choose sigma B to be rho B. Then this cancels out of this inequality. It's not relevant. And then we are left with rho A less than or equal to 2 to the minus lambda. So we're looking for the largest eigenvalue. And this, indeed, the min entropy, that is actually a very old definition in cryptography. The min entropy of a distribution is the minus log of the largest value of this probability distribution. And so we just generalize it to the largest eigenvalue. H max, this is a bit of a different case. I think he defined it simply as the size of the support of the density, so the dimensionality of the support of the density matrix, which in the classical probability would be just the cardinality of the support of the measure. That's not quite the thing here. So if we get rid of sigma, so then basically this goes away, and what we are left with is square root of rho trace norm. So it's just a trace. It's just so it's just the sum of the square roots of the eigenvalues, and then squared and take the log. And so this is a kind of a Rényi entropy actually. Rényi entropy of 1/2. So H max of a single system is H 1/2 or probably S 1/2 in what I wrote before of rho A. So it's kind of similar. It is definitely dominated by the size of the support, but it's not equal. It's a kind of an approximation of the H max that Fernando had. But the smoothing takes care of this. So I can assure you that one of the good things of the smoothing is that that somehow it makes all the Rényi entropies for P larger than 1 related, and all the Rényi entropies for P less than 1, they become related. So this is just a side remark. Don't ask me to go on about this. This definition is maybe the most hard to swallow, but it's there essentially just to make this an identity. So in fact, in Thomas Michel's thesis, I think he uses this, what I wrote as a fact, he uses as a definition. He says H max is simply minus H min of the complement, period. And then he proves a theorem that this is the formula. So that goes a little bit far, I think, but fine, that's how people do this. So then now next, sorry.
The pure psi ABC that you write there.
Yeah.
Looks like C is some kind of purification
Yeah, that's equivalent. You can say, think of it this way, right? Yeah, of course. But to me, it gives the wrong message because it says, oh yeah, you have to find a purification for rho AB. But in the situations that we're dealing with over here, we are kind of naturally given a pure state anyway, and we're just looking at various reduced states. So it's a bit more democratic also because it doesn't distinguish between the rows of rho AB and rho AC, if you want. But yeah, it's equivalent. It's the same thing. Yeah, I'm a bit reluctant to remove this part here too much. Okay, so let me keep this diagram. So this swapping thing that we leave it, the additivity proof, we don't need it. Yeah, so I guess I just have enough time to show you a little bit of a flavor of how you if you have if you have a code. Oh, sorry, I have to go back to that, of course. I mean, sort of the first step is always, I mean, all these entropies, their value relies in that you can somehow relate them to the task at hand. So, it's a bit sad, but I will delete it after all. So the task at hand, I just want to remind you, we have our channel. I mean, I just need to draw some. What do I need? Let's put A here, or A. Oh no, A is not good because that's the code basically. And then we have the. Yeah. Okay, so I see. I might, of course. I mean, I should at least follow my own philosophy, right? So we have the Vn. We need, of course, En. But instead of the degrading map, I mean, that's at the moment it's not the most important thing. We need the decoding. So also the decoding is has some kind of Steinspring form. So I can V, W, I don't know, can I write an X? I don't want to use the same letter. So there comes out an S. This is the one. Here we have our sigma, which is close to phi L, right? So this is our up to epsilon. So the channel also produces this environment. The decoding also will produce some stuff. I mean, actually, when you look at quantum error correction, there's always some register that contains just the noise. So we have to get rid of this. And this is some kind of, so again, I don't want to use F, so let's use G. So it's just some register, junk. And so, one way I mean, now this purified distance again comes in handy because sigma is just a reduced state of some big pure state, right? So sigma is trace over En and G of some psi, and phi L, well, that's also a reduced state of phi L tensored with some arbitrary, with some suitable state here. So they're both pure, and so that the fidelity, that the purified distance between this psi and phi L tends to 0 on G(En) is also less than epsilon. And so this is a consequence of this Ullmann, that I can always invent a purification of phi L, which necessarily is of this form, with the same purified distance. And so the first thing we have to do is, actually I want to yeah. Oh, I see. So we need to worry a little bit about getting the L into the picture. So we have to use the fact that sigma, or rather its purification, is close to this maximally entangled state. And so that's basically, this is the only point where I use the smoothing. I really literally interpret this as an error. H min epsilon it's a maximization. So there is one state in the epsilon neighborhood of sigma, by definition, which is this phi. So this is larger than H min of R given ENG of phi L. But you see that, well, there should be phi L tends to 0, really. No, because it's this one here. But you see this GE, it's just factored off. So this is a product state, and R is, by definition, in this state, is maximally mixed. So this is equal to log L. So this is this is our foothold, because this is from where we will try to bound log L in terms of entropic quantities.
Sorry, is sigma a state of SR?
Yeah, sorry, it should be psi. Sorry, yeah, of course. Yeah, okay, so let me put it this way. So then step 2, actually let's put it differently. We want to get rid of this G because that makes only sense once we have a decoding. So in good information theoretical manner, we would like to roll back here. We would like to talk about a state that is just the output of a channel, period. So there we use some kind of version of Strong's additivity. So this here is less than or equal than H min epsilon of R given En. And this now I can actually interpret on this level. The whole B system doesn't really play a role at this moment anymore. And so let's call this phi. So phi is identity tensor V tensor N acting on some script phi. So, and this is because of well, I don't know. There probably you can invent. I mean, it's a kind of monotonicity property, right? If I lose information, the conditional entropy goes up. So this is something that I used for Neumann. or you might just call it strong subadditivity for the mean entropy. So this is another, there's more properties. So this is H min of A, B, C, or let me put X, Y, Z is less than H min of X, Y. And the same for epsilon here. So this is exercise for epsilon equal to 0, and then epsilon larger than 0. And the same for H max. Yeah, so you have the same thing, you just write max here, you have the same inequality. This is a bit confusing at first because you think, oh, H max is some kind of a negative of H min, but of course there is also this complementation. And dropping a system in the complementary system, I mean, dropping a system means giving it to the complement, right? So maybe that makes sense. So this is a general property of this mean entropy. In fact, it's from the definition, you should really be able to get this here straight away. It's literally just reading off from the definition.
Sorry, Andreas, I need 5.
Yeah.
Over the kind of B system. There's a B and then there's a.
Aha, so this is kind of, yeah, so maybe this is, I should, it's yes and no. So I write phi because I want to remind you that there is this big pure state. But of course, this here, I'm referring to the partial trace over everything that is not mentioned, basically. So this is a kind of a general point of notation when you read reasonings with these mean entropies. It's good practice to keep track of this big pure state because you might want to complement, which I'm going to do next, actually. So this is equal to minus H max of R given Bn with the same phi. But of course, yeah, so literally looking at the definition, I have to partial trace and then look at the reduced. Fair enough. So now, I'm losing I have to give you this something, right? So anyway, you're getting the hang of it. I mean, one of the main reasons why these definitions were introduced in such a way and why they are successful is because they do capture some properties of what we know from the entropy. So now we use the degrading. So because Bn, that's what Bob gets, so we know that if you have a degradable channel, then we can apply this, well actually I don't want to use the degrading CP map, I want to apply the corresponding isometry because that preserves everything here. So here I was using the complementation, so now the degrading, and that's this W that maps B to E prime F, right? And so we get, so I just start again. So we have log L is less than or equal to minus H max of epsilon. We have our R, Bn, right? And instead I write E prime n, F to the n, and of course this refers to a state now. So let's keep track of what the state is. I have still my phi here, V tensor n. Then here is the W tensor n, E prime F. So the phi I was referring to before was here. So this is phi. I'm running out of letters. Give me a favorite Greek letter that is not psi, because I think psi I had already before, no? Yeah, exactly. Huh? Huh? Chi. Okay, let's use chi. Why not? Good. Yeah, upsilon I don't like. It's kind of, it sounds like I make a mistake all the
It's
time.
from the Big Bang Theory. Give me a funny Greek letter.
Good. I wanted your favorite, but okay, fine. So this refers to chi, right? But I'm just using identity. I mean, this is it's implicit. I mean, actually, by inspecting the definitions, you can see that they are invariant under unitaries and isometries. So, of course, I erased this board already twice now. There was this beautiful line on the bottom where I was showing the manipulations for the additivity proof, just with entropy. So the one thing that we are missing is the chain rule. So unfortunately, this doesn't really satisfy a chain rule, but it satisfies a kind of an inequality that looks a bit like a chain rule. And it goes, so this, I mean, I'm not proving any of this, actually. I mean, the best place to look this up is in Marco Thoma-Michel's PhD thesis, where it's all beautifully developed and closed. So what do we want? We need an H max of x, y, z, and with an epsilon. Oh, I hope I wrote this somewhere correctly. Okay. So it's not an identity, but you have inequalities. It's less or equal than H max of sorry, this should be a Z, no? I'm sorry, what am I doing here? I need a y given x. So it's worse because, of course, we have a smooth, we have this epsilon sitting around here. So these inequalities, I have to basically put the correct epsilons here. So there are three values that I have to trade off. And it turns out that I believe it's something like this here. And then there is a okay. Sorry about this. I'm getting, so it's something like this here. Log 1 of a delta. No, I should have. I didn't copy it in the notes here. So I can't tell you which particular lemma it is in the thesis, but you find it. I mean, if you really look it up, there is a whole chapter on chain rules. Chain rules, because there's more than one. So it's like with the entropy. So since we have a choice, see, you have this inequality that involves 3 terms, and so there are potentially 8 permutations. And they discuss all of them. I mean, he discusses all of them, referring to a joint paper with Renato and some other students of the group. And so each of them requires a slightly different jiggling of the parameters. So this kind of the art is then to get a truth, to put the epsilons here in the right way. So of these 8, the one that turned out to be useful here is this one. So remember, ultimately, we started off already with an inequality. So the fact that we have an identity is gratuitous. I need an inequality. I want something less than equal. So I get H max delta now of f to the n e prime to the n. And then I get an a minus H max of of a slightly bigger epsilon of A, sorry, this R, F, N, B prime N. And so now I should really try to find a way of closing this.
Is delta related to epsilon itself?
No, delta is just another parameter. Choose it. Actually, what I mean, this there's probably something else wrong here because this here should not be bigger than 1. So there might be also an order log 1 over 1 minus epsilon minus 2 delta, so that you kind of you shouldn't make this too big here basically, and this one not too small. But it's just, I mean, these kind of inequalities, they are true for all epsilon and delta. The way if I could have remembered it correctly, this extra term, then it's not evident. I mean, it uses the definitions in a very non-trivial way, and that's one of the reasons why you don't get identities. You just get inequalities. I just realized I was wrong to go the grading directly. So let's go back to this one here for a moment, actually. So because already here we used some inequalities. I mean, I hope you felt sufficiently uncomfortable all the last few lectures that always I'm just using inequalities, right? I mean, ultimately I want to evaluate some asymptotic limit. Why do I just bound? And so, of course, a priori, I never know how good the bound is. I mean, and then sometimes I'm lucky that in the asymptotic limit, it's a decent bound, or it's even equal to the lower bound. So here, at least, for once, we know that we haven't lost too much. So it turns out this one here, this number, horrible as it looks, I mean, it is definitely because you have to solve this minimax optimization problem, and that's in practice completely out of the question. You won't do it. This here is actually very close to the maximum here, and so there's this kind of just a side remark that I just want to put in because I think that's very important to realize that up to this point we haven't lost much. So this is I think I should refer to a paper by Buscemi and Data, 2011, roughly. I don't have the reference here. I mean, it's in the book, but I don't want to find it now. So you prove that log L of n epsilon plus eta, let's say, is larger or equal than, what do I have here? H min of R given e to the n minus order log 1 over eta. So again, eta is just a parameter, a new parameter that we will choose suitably. So whatever epsilon is, just choose eta small enough so that epsilon plus eta is at least less than 1. Or if epsilon goes to 0, epsilon plus eta also should go to 0. And then we have, here we have this min entropy. This is just another way of writing this guy here. With respect to any state, right? So there's no assumption on what the state here is. So just pick a test state, construct this phi, and try to evaluate what this here is, epsilon. And then you have, so this epsilon is some kind of error, and this eta also contributes to the error in some concrete way. And so that's very important. So we don't lose too much. I mean, this is just another additive term. If eta is not decaying too fast, then we're fine. So it really boils down to understanding the maximum value of this over all possible input states. And this is the problem that we cannot solve in general, but for degradable channels. And for degradable, we do this here. So, and at this point, you need a number of further tricks. So I will just do something here. So first of all, this thing depends only on the input density. I don't know if I have it somewhere here. This is this rho A to the n. And in fact, the state is a linear function of rho n because I have to apply the channel and then this W. and I can show that it's maximized on permutation, Sn permutation symmetric rho an. So that means that rho an commutes with the permutation matrices of the n systems. So this is kind of the key. So I should ask you to compare with the concavity of S of f given E. So for me, this is a very nice point about this argument. In the proof of additivity, I was for the capacity for this Q1, I was using the strong subadditivity to break up a term like this into n upper bounded by n terms. If this was an S here, I could just put less than or equal than sum of S of Fi given Ei. Somehow you can't just do this so easily with these min and max entropy. It's not a good idea, let's say. But an equivalent manifestation of strong subadditivity is the concavity. In fact, this is exactly how Lieb and Ruskay proved it first. Their main lemma is the concavity of S of f given E in the state as a function of the density. And so this concavity means that whatever state you have, of course it's also permutation invariant because it's just a local unitary. So averaging over all permutations can only increase the entropy. Now this max entropy is not quite as kind to us. It's not concave, but it's concave in this particular situation. If you just want to symmetrize over permutations, then you can do that. So, and this means that this guy here is already very close to an entropy. And then this one here turns out to be bounded by a constant for epsilon plus 2 delta less than 1 over root 2. And then I really regretted that I won't have time to tell you where this root 1 over 2 comes from. But this one is kind of uses this complementation rule because I have this minus h max. I can just replace E prime by E because that's the only other remaining system, and I get h min. And then, so actually that's the reason, because, so minus h max, so let me put this in shorthand, Rf given E prime is h max, h min of Rf given E, and this is here some, let's call this T here, T, and it turns out this is less than or equal up to some constant terms of h max with E plus some constant terms. That I don't write, they depend on T and they explode when T gets too large. So we get rid of this in a very similar ways for the entropies. And this one here, we go to a permutation invariant state. And then from there, so there's a bit of a long road, but that's kind of the most important one was to go to this permutation invariant state, is to go to H max of delta of Fn En of some rho A to the tensor power n. And so this is this guy here. So I don't want to explain where this comes from. So these permutation invariant states, this is a kind of a Definetti argument in the sense that if you don't look too closely, a permutation invariant a permutation symmetric state is well approximated by, it looks like a tensor product state, a tensor power state. And at that point we won because this here is less than or equal than n times S of f given E prime, I guess, for the same row plus order square root n. And this sort of statement actually it's even equal here, plus minus. So up to order square root n terms, this is a fundamental property. This is kind of the last and one of the most important properties of this max entropy. There is a regime in which you recover von Neumann. So maybe this you can think of it as we had yesterday and the day before. I was putting a lot of emphasis on the fact that the Rényi entropies, they converge to the von Neumann one when the p or alpha goes to 1. And somehow this is the analog here. So when we evaluate this smooth min entropy or max entropy on a IID state, tensor product, then it gets then the value, it scales with n with the copies, and it's the entropy up to lower order terms. So this is the limit in which we can recover the von Neumann entropy. And this is true for all epsilon, for all delta. So kind of this epsilon that we had initially here, that left some trace here in t. We had to choose delta very small, but it was not important that anything of this goes to 0. So the net result, I just want to write this down before you cut me off. So you get this L tilde of n epsilon is less than or equal than n times q1 of the channel, because of course we will simply replace this by the maximum one of these rows, because a priori we don't know which one pops out of the analysis, plus order square root n, and I think to be completely honest there will also be a log n eventually. For epsilon less than 1 over root 2. So I don't get it quite for epsilon less than 1. That has to do with a technical point here, but let's forget about this. So as soon as the error is small enough, and it's not even that small, so here's the exercise. 1 over root 2 is the error of a 50-50 erasure channel. I mean, E1/2 of dimension L. And so that it doesn't have to, I mean, for any dimension, of course, I can define this erasure channel. However large L is, this you will have, if you just stick in the state, you can always send a state of size L that has this error. So as soon as you're below this, so this is a kind of a cloning bound. As soon as you're below that, sorry, this is a log. The rate is bounded by the capacity. Because when I divide by n, this will go to 0 already. And this is constant, right? So this is exactly, so it's like a strong converse, only that if the error is really big, then maybe something happens, but I don't know. And I stop here, I think, because we are getting hungry, no? It must be time. Yeah, it's high time, actually. So, yeah, so thanks, and maybe you ask me questions if you need more clarifications. No.
So this is Andreas' last lecture. Andreas handled a very difficult subject. At least for me, it's a very complex one. One could see him striving to make things very natural. You know, his choices. He could have just written equations one after another. But I think it is in a discovery mode, making every step very natural.
If you want the equations,
Yeah. So I think this is those of you who aspire to be teachers, I think there is a little bit lesson to learn, you know, to make the audience feel like discovering along with you. So Andreas, thank you very much for this. Very nice.